Hi guys, it's me, Mrs. Villa, and I know since we had some technical difficulties in third period, I wanted to make a quick video to hopefully highlight some of the things that we were dealing with today when we were talking about infinite sequences and series. So first things first is I just want to remind you guys about how we can tell whether a geometric series is considered convergent or divergent. And the key is to pay attention to your ratio. If you have a common ratio, that means it is a geometric pattern, but when something is geometric, it can either be defined as a convergent pattern or a divergent pattern. And basically, the way we can tell which one it is if our ratio is between a -1 and 1, we would say that it is convergent. If our ratio is bigger than 1, or if our ratio is less than a -1, we would say it is divergent. This is important because you can only find the infinite sums if you have a convergent geometric series. If you have a divergent geometric series, your answer would simply be something to the effect of the sum does not exist, or you could say there is no sum. So how can we tell in an actual scenario? Well, visually, you can tell something's convergent if as you increase down the pattern of your series, if you start to notice that your terms are leveling out. Okay, if you start to notice that your terms are starting to shoot up as you go further down your series, that would be divergent. You can also have it look like it's leveling out in this downward pattern. That would also be convergent. Or you can have it dive down, and that would be divergent. Okay, so the key is the ratio. Remember, to tell if something in general is geometric, you check for a common ratio, and then if that ratio is between -1 and 1, it is convergent. All right, so we're going to look at a couple problems. We're going to start off with example 1, and the first thing we wanted to do was tell whether or not it is convergent or divergent. Now notice, I did in this case tell you it happened to be geometric, but if you weren't told that, you could simply find it by checking your common ratio. So in this case, when I go and I do 24 over 20, I get a common ratio of 1.2. In fact, I would see that common ratio if I kept checking my ratios. 28.8 over 24, I also get that 1.2. Now, since my ratio is greater than 1 or less than -1, in this case, it's greater than 1, I would say that this is a divergent, or it diverges. Okay, that would mean that I cannot find the infinite sum. In this case, if I were asked to do so, I would simply say the sum does not exist, or there is no sum. However, then I look at example 2, and let's say, again, I take my second term over my first. I'm going to get a common ratio of, not 1/2, 1/3. And since my ratio, 1/3, since that is between a -1 and 1, I would say that this must be a convergent, or it converges pattern. Okay, 1/3 is between -1 and 1, therefore it must be convergent. I could then use a formula that I'll talk about in just a moment to find that infinite sum of this convergent geometric series. The formula that I was just referencing about how you can find the sum of an infinite amount, an infinite geometric series, is this right here. So A1 over 1 minus R. Now you can only do this if your ratio is, the absolute value of ratio is less than 1. Remember, another way to think of that is if your ratio is between a -1 and a +1. If, however, your ratio is not within that range, then you would say that the series has no sum. All right, so let's go down here. Let's look at example 1. So I found my ratio, and sure enough, I can see that it is geometric because I get a common ratio of 0.8. So in this case, I could say my ratio equals 0.8. Now my question is this going to converge or diverge? Since my ratio is between a -1 and a +1, I could say that it is going to converge. And that means that I can find the sum. Now I'm going to use this formula that I have listed just right above. I'm going to find the sum. My A1 in this case was 5 divided by 1 minus my ratio in this case is 0.8. Now, I'm going to always show my ratio in parentheses. The reason being is because if you ever have a negative ratio, it can be a little tricky down in that denominator when you see the 1 minus. All right, so I'm going to get 5 over 1 minus 0.8 is just 0.2. And in this case, I'm going to get 5 over 0.2 should just be 25. Now notice I could do this because I was able to give the green light and find the infinite sum. However, let's say we were to look at a problem like example 3. In this case, I find a common ratio, and in fact, I am getting a common ratio. Ratio equals 2. So this is geometric, so that's good. But the issue is, since my ratio is not between a -1 and 1, 2 is not between a -1 and 1, I would say that this is going to diverge. If it diverges, it means we can't find the infinite sum. And so we would say, you could say there is no sum, or you could say the sum does not exist. Hands down, the most common mistake that people will make with infinite geometric series, if you're afraid you're going to make it, listen up, make a little note to yourself. Hands down, the most common mistake I see people make is people will get their common ratio here, and then they will just automatically go and plug it into their infinite formula, and they'll get a sum of -3. People will do this and be like, sweet, got my infinite sum, there we go, -3, and walk away. But none of this should have even happened once we noticed that it was actually a divergent geometric pattern, okay? Avoid making that mistake and you should be good. The only other thing I want to draw your attention to, and I mentioned this in class, was that sometimes your geometric pattern won't be listed out for you as it was here in example 1. So what you can do is if you have the rule or the summation notation as here in example 2, you could actually use this rule and plug in 1, 2, 3, etc. And you could actually get your series written out, okay? Once you have that, you can check the ratio and determine whether it's convergent or divergent, just like we did in example 1. So if I do that in this case, I would do 2/3 over 2. I could also think of that as 2/3 times the reciprocal. So my ratio in this case would be 1/3. Since my ratio is between a -1 and 1, I would say it converges, right? And that means I have the green light to go and find the infinite sum. So I would do A1, which is 2, divided by 1 minus 1/3. So that would basically turn into 2 divided by 2/3. And when I divide that, I'm going to get an answer of 3. Again, I could do this because I verified the ratios between -1 and 1. Also notice that if the problem were given to you like this up in summation notation, you're not necessarily given A1 flat out, and so listing out your terms, like your first term, second term, third term, sometimes can be helpful not only to check your ratio, but it can be helpful because you need to know what that first term was for your infinite sum formula. All right, now I mentioned that I really encourage you guys to always put your ratio in parentheses. This is the last problem I'm going to do here, and I want to show you why. So in this case, if I wanted to determine my ratio, I could do -5 over 20. So that'd be like a -1/5. Some people prefer to work in decimals, so you could say a -0.2. But regardless, that's my ratio. Since my ratio is between a -1 and 1, I could say that this is going to converge. And again, I get the green light now to do my infinite sum. Now, when I do my infinite sum, it's important that when I do my work, I do my A1, which was 25, over 1 minus my R. What a lot of people will do here is they will just write the 0.2, even though their ratio, you guys, was a negative. So this is part of why I told you I always put my ratio in parentheses so that I can see whether it's positive or negative. Now I can see that when I actually do my arithmetic, it's going to turn into like a 1 plus 0.2. So it's 25 divided by 1.2, and in that case, I get 20.83. So important putting your ratio in parentheses so that if it is a negative ratio, you can still see that in the formula when you plug it in. All right, I hope that helps with infinite series, telling whether something converges or diverges, and then using the infinite sum formula if it's a convergent pattern. Otherwise, let me know if you have any questions, and have a great day.